Okay, welcome back. So, in the last class, we have discussed the crystallographic directions, particularly for cubic crystals, and then we have actually also introduced the concept of equivalent directions. So, for instance, for a cubic crystal, you have 1 0 0, 1 bar 0 0, 0 1 0, 0 1 bar 0, 0 0 1, 0 0 1 bar. All these are equivalent directions, and these are called a family of equivalent directions, and the family of equivalent directions is represented by this sort of a representation. You have Macaulay sort of a bracket and then 1 0 0, and all these permutations of these three indices will give you the equivalent directions for cubic crystals. And please note that this way of representing equivalent directions will only work for cubic crystals. For other crystals, for instance tetragonal crystal, it may not work. Okay, it does not work. So, so this definition of equivalent crystals is what we are only you should keep it in mind, that it is only right for cubic crystals. So, for instance, you can say that by that definition 1 2 3 direction in a cubic crystal must be equal to 2 bar 1 3 bar or 2 1 3 bar, 2 1 3 and so on. Alright. So, now having discussed how the crystallographic directions are shown in a cubic crystal, now let us look at hexagonal closed packed structure. So, suppose if you take a hexagonal crystal and which has 3 lattice vectors A1, A2 and Z, right. Z is the outer plane direction, and in the base plane or basal plane you have these 2 lattice vectors A1 and A2. Alright. So, this can also be our one of the definitions of our unit cell for a hexagonal closed packed system. And now let us look at this particular direction, that is the projection of this line, this guy onto A1 axis, A1 vector is 0, that is why 0, 1 bar because it is in the negative A2 direction, and the projection of this guy onto Z axis is 0, so that is why this direction is 0 1 bar 0. And then if you take this guy, again 1 bar 0 0, but if you take this direction, then you have 1 1 0, right. But you know that all the how do we say the equivalent direction? Basically, when you are moving from this position by same amount, you should meet the another atom, right, by the same distance, by moving in the same distance. So, here this distance and this distance are the same. So, by definition of our equivalent directions, these three should be equivalent directions, but when we are talking about the equivalent direction definition, as we have discussed in the cubic crystal, the indices, the Miller indices, the numbers should be the same. So, you have 1 0 0, so you should have 2 zeros and 1 1s in any combination, but here you have 2 1s and 1 0. So, if you have this representation for crystallographic directions in hexagonal systems, you will not be able to use the permutation of same set of indices for representing equivalent directions, because the equivalent direction here by looking at, you cannot say that these two are equivalent directions unless you actually draw and show that. So, that is how the representation of the crystallographic directions is actually the equivalent representation is actually breaking down. So, this is the problem with 3 index notation, because some of the equivalent crystallographic directions will not have same set of indices like these 3. So, that means the permutations are not possible for equivalent directions if you are using such a definition A1, A2 and A3. Alright. So, now how do we circumvent this problem? How do we fix this problem? So, the problem with the 3 index notation is usually circumvented by a 4 axis or Miller-Bravais coordinate system. So, you have to do some modifications to your coordinate system. So, instead of having 3 indices, now you can have 4 axis system. So, previously you have A1, A2 and Z. Now, we introduce another axis A1, A2, A3 and Z. So, now you have 4 indices representation. So, A1, A2, A3 axis are all in the basal plane, and the fourth Z axis is the outer plane direction, that is in the thickness height direction. So, the first 3 indices, so for 4 directional indices notation is U, V, T and W. First 3 indices U, V, T are the projections along the axis on the basal plane, and the third index is the projection onto the Z axis. Alright. So, now how do we actually, is there a possibility to convert from 3 axis notation to 4 axis notation? Let us say our 3 axis notation is represented by u dash v dash w dash. How do we go from this notation to u v t w? So, this is one of the prescriptions, but there can be, people can come up with different prescriptions if required. So, one of these prescriptions is that the u in 4 index notation is related to the 3 indices notation as 1/3 2 u prime minus v prime, v is 1/3 2 v prime minus u prime, and t is negative of u plus v. So, that means the third index should also always be, in a 4 index notation, should always be negative of sum of the first 2 indices, that is important, and w is directly w prime. Okay. So, this is how one can transform a 3 index notation to a 4 index notation. Once you do that, all the equivalent directions are expected to be having same set of indices. We will see that. So, how do we talk about this reduced coordinate system? So, the reduced scale coordinate system may be helpful instead of using with full scale coordinate system to plot the crystallographic directions in HCP. How do we go about doing that? You discretize the basal plane in such a way that every intersection of 2 axes is trisected by the other axis. Okay. So, you basically trisect each of the coordinate axis, and along the z axis also you trisect m at m and n. M is at a distance 1/3, n is at 2/3, m is at 1/3, n is at 2/3, and this point is as 1 in the 1/3 of the lattice vector dimension there. So, here this is how we do the trisection. So, this is the trisection of coordinate axis along A2, and that is A1 and A3, right. Now, if you have that, now we can actually see how do we use this to represent the coordinate directions for hexagonal closed pack structure. So, now let us see how do we convert 1 1 1 direction in a hexagonal crystal to 4 index notation, and then draw the direction in both the systems and show the equivalence. That is the problem that we have to do. So, this is u dash v dash t dash, sorry, u dash v dash w dash, and that you have to convert it into u v t w, right. So, the transformation from u dash to u is given by this formula. So, it will become 1/3 1/3 minus 2/3 and 1. So, 1/3 1/3 minus 2/3 and 1. So, that should be written as 1/3 1/3 2/3 bar and 1, but of course, again the minus should not be written as minus, but you can see that minus of 1/3 plus 1/3. So, it should always, the third one is, you really do not have to calculate t, or you just have to calculate u and v, the t will be negative of sum of these two, and then you need to show that on the hexagonal crystal lattice, hexagonal unit cell. Well, let us show that. So, this is 1/3 distance. So, we have to move 1/3 along A1, that is your 3 index notation 1 1 and 1. So, that is our 3 index notation. 4 index notation you have to move 1/3. So, that means along A direction. So, that means from there to there and so on. This is our 1/3 along x axis, 1/3 along A2 axis, minus 2/3 because A3 is shown in this direction. So, minus 2/3 is this, and then this is 1 unit. So, but the way to represent that is actually when we are representing coordinate, so the crystallographic directions, you do not work with these fractions, you try to convert into smallest integer. So, multiply everything with 3, that means 1 1 2 bar 3. Here 1 actually means 1/3 distance on your crystallographic plane. So, that is why your 1 1 2 bar 3 means 1 means 1/3 along that line in 4 index notation, again 1/3 and 2 times, right, 1 2, that is 2/3, and 3 means 1/3 2/3 and 3. So, that means this is 1 2 3. So, 1/3 is 1 unit when you are talking about 4 index notation, and both of them are showing the same crystallographic direction. All right. So, having discussed how do we represent the directions, the next important aspect that we need to define is the crystallographic plane. So, the orientation of planes is described similar to directions, except for hexagonal system, crystallographic planes are specified by 3 Miller indices H, K, L, and they are enclosed with parentheses. So, H, K, L represents the representation of crystallographic plane, and H, what is H and what is K, what is L, we will see, right. And any two parallel planes, so this is for 3 index notation. For 4 index notation, you have to have H, K, maybe W, L, 4 index notation, right. But we are only first we are going to discuss about 3 index notation, and then 4 index notation, the same philosophy that we have used for directions can be applied to planes as well. And note that any two parallel planes are equivalent and have identical indices. Two parallel planes are equivalent, they have identical indices. Okay. So, how do we determine these indices, Miller indices for crystallographic plane? Now, first we need to check if the plane is passing through the origin. You have a crystal cell, a unit cell, and you need to check the plane for which you want to write the Miller indices, whether it is passing through the origin of the unit cell that you have chosen. So, if the plane passes through the select origin, then what you need to do? You need to either another plane parallel plane must be chosen within the unit cell, another parallel plane must be constructed within the unit cell by translation, or you change the origin, you have to choose a new origin. That means the basic guideline is that the plane should not be passing through the origin. If at all the plane is passing through origin, because we said all parallel planes are equivalent and have exactly same indices, you just have to translate the plane such that it is parallel to the original plane, and then it is not moving, it is not passing through the origin. All that we need to do is ensure that the plane is not passing through the origin. And at this point what happens? The plane is going to either intersect the coordinate axis or it will be parallel to the coordinate axis, because if originally if it is parallel to one of the coordinate axis, by translation it will not become non-parallel, right, it will still remain parallel to the coordinate axis. So, at this point of time, your plane should either intersect one of the axis or it is parallel to one of the coordinate axis. And the length of the intercept, if at all it is at what length it is intercepting. So, the length of the intercept is determined as a fraction of the lattice parameter, right. You have to write the length of the intercept as a fraction of the lattice parameter, and then you have to take the reciprocals of those numbers. So, first you have to identify the intercepts and write them as fractions of the lattice parameter. So, if it is intersecting at the half the distance, then you have to write 1/2 a by 2. If it is intercepting at a distance a by 2, then you have to write 1/2, right. And then you take the reciprocals of them. So, the reciprocals of the numbers are taken, and if a plane is parallel to x axis, that means it is intersecting x axis at infinity, right. If it is parallel, then the reciprocal of that will be 0, right. So, now again scale the indices to the nearest integers. Sometimes you do not actually do the scaling, but usually in this class we will do the scaling to the nearest integers, and then collect the numbers and put them under parentheses. That is how you will identify crystallographic Miller indices for crystallographic planes. So, this is the definition representation for crystallographic plane, and the family of crystallographic planes are represented or designated with curly braces. Okay. In a cubic system, if you are looking at cubic system, the planes having same indices regardless of the order or sign are equivalent for cubic systems. They need not be parallel, but they can be equivalent planes. And hexagonal crystals are expressed in 4 index system, wherein they are represented H, K, I, L, where I is equal to negative of H plus K. Alright. So, now let us look at this particular system and let us try to see whether we can identify the Miller indices for this plane. You can see that this plane is actually passing through the origin. This is our origin, it is actually passing through the origin. So, the first check to be made is to see whether the plane is passing through the origin. If the plane is passing through the origin, what is that we need to do? Either change the origin or move the plane, translate the plane. So, what we have done is we have actually changed it. So, initially here, now we have moved our coordinate system from this point to this point. So, that means you have moved the origin, but keeping the plane the same. So, now O dash is your origin and x dash, y, z dash is our new coordinate system. Now, the plane is not passing through origin. Now, let us look at where this plane is intersecting x axis, y axis and z axis. Is this plane intersecting x axis anywhere? It is actually parallel to x axis, so it is not intersecting x axis. Where is this intersecting y axis? So, this is intersecting y axis at this point, so that means negative a. So, let us say this is a, it is intersecting at negative a, and z axis it is intersecting at positive a by 2, right. So, x intercept is parallel, that is why infinity times a, and y axis it is intersecting at minus b, and z axis it is intercepting at c by 2. A, B, C are your lattice parameters for instance, and then you write that intercept as a fraction of your lattice parameter. So, that is why I am writing infinity, minus 1 and plus half, and then you need to take the reciprocals of them 0, minus 1, 2. Do we need to do any reduction, because there are no fractions, so there is no need for reduction, and hence the enclosure will be 0, 1 bar and 2. So, that is the representation of that plane. Okay. And now let us construct another plane 0, 2 bar 1. So, in order to construct, what we need to do is first we need to find the intercepts. What are the intercepts? Intercepts will be the reciprocals of them, right. When we are constructing, we have taken the intercepts and then taken the reciprocals of them to represent the mirror entities. Now, in order to find the intercept, you need to find the reciprocals. So, that is infinity, minus 1 by 2, 1. That means, this plane is going to be parallel to x axis, going to intersect y axis at minus half and z axis at 1, right. So, implies parallel to x axis, y axis at minus half, z axis at 1. So, that is, this is B. So, this should be intersecting y axis at minus half and z axis at 1. So, that is our plane 0, 2 bar 1. So, equivalent planes. So, this is all parallel planes are equivalent. So, that is also equivalent, all parallel planes, and they will have same set of indices. And in a cubic system, for instance, a plane and a direction with same indices are orthogonal to each other. That means, if you take a plane 0, 0, 1, because this plane is intersecting z axis at 1, but it is parallel to x and y axis. So, that is why these two indices are 0, 0, 1, and the normal to this plane, the direction, crystallographic direction that is actually normal to the plane, will have exactly the same indices as the indices of the plane itself, but so the normal direction should be different, shown with a different brackets. So, in a cubic system, plane and direction with the same indices are orthogonal to each other. That is what orthogonal means. To a plane, if something a direction is orthogonal, that is what is called normal to the plane. All right. So, now let us define something called linear density. What do we mean by linear density? So, the linear density is defined as the number of atoms centered on a direction vector. So, we have defined a crystallographic direction. So, on that direction vector, how many number of atoms are centered divided by the length of the direction vector. That is what is called linear density. So, if you take a 110, if you take a hex FCC material, then you have 110 direction is this. How many atoms are there on 110? There is one full atom, and this atom is part of another atom. So, this atom is another unit cell, this atom is also part of another unit cell. So, half of this guy is present here and half of this guy is present here, and effectively you have 2 atoms lying on that direction. So, 2 atoms divided by the total length. If it is r, then these face centered atoms are these atoms are touching each other. So, this will be 2r and this is 2r. So, then total length is 4r. So, the linear density is 2 atoms by 4r. So, that means 2 by 1 4r, that is 1 by 2r. So, that is how, if you look at, that is how this looks like. So, that is about linear density. Now, when we have defined crystallographic planes as well, and hence we also have to talk about planar density. What do we mean by planar density? Number of atoms centered on a plane divided by the area of the plane, right. So, if you take this particular plane, what is this plane by the way? It is intersecting x axis at 1, y axis at 1 and parallel to z axis, and hence this should be 1 1 0. This is what you call 1 1 0 plane in an FCC material, face centered cubic structure material. And then let us look at the planar density. So, this is how the atoms are arranged, and you can see that in this plane this atom is this part of the atom is available, this part of the atom is available, this part and that part. So, effectively these two together one atom, these four together another atom, right. So, there are effectively two atoms available divided by the area of the plane. So, you know, if this is A, you can find out the relation between. So, what is this distance? This distance is 4r, right. Yeah. So, this distance is 4r and you need to find out this area, and that means this is A, this is A. So, you can find out what is the value of A, and then that will actually be the area will be 8r square under root 2. The planar density of 1 1 0 plane for FCC is 1 by 4r square root 4 root 2 r square. So, the knowledge about this linear density and planar density is one of the important aspects to be known, because the planar density and linear density are going to give us some information about the deformation mechanism when we are talking about plastic deformation in materials, and hence it is extremely important to know what are the planes in a given crystal structure or a given unit cell which are most densely packed, that means which are having highest planar density or lowest planar density. What is the direction in which you have maximum linear density? That means that is the most closely packed direction. So, it is important that you need to know what are the most closely packed planes and most closely packed directions in a unit crystal lattice or crystal structure. So, the knowledge of the linear and planar density is important for understanding crystallographic slip mechanisms during plastic deformation, and for every crystal system like BCC, FCC and HCP, it is important to know the densely packed crystal plane and the crystal direction. Please check that for BCC and FCC, what will be those close packed directions and close packed planes. Okay. With that, I will close here, and in the next class we will look at how these we will also see the most densely packed planes, some of the other most densely packed planes, and all other details about crystal structure in the next class. Thank you very much.